Chem office hours. We are here weekly at this time. My name is Corinne. I run Chem with Corinne. I'm a teacher. A long time ago, I was a chem major. I loved it so much. I got a few more degrees in chemistry, and now I do this for fun. Yeah, I actually think chemistry is fun. So I'm excited to be here with you all for the next hour, just answering any and all of your chemistry questions. So the way this works is I just want you putting all those questions in the comments. The more interactive you are with this feed, the better this office hour is going to be for you. You have to ask questions. You have to remember that in class too. And if you have not checked out Chegg yet, Chegg has so many resources like these 11 weekly lives to help you out. Amazing resources. I'm going to be using some of their practice problems. And when you check out Chegg, you'll be amazed. It's not just an answer with any of these practice problems. They're actually taking the time to explain it. So you're actually learning as you are studying. Definitely check out Chegg. Check out their resources online. Check out their socials too. Lots of great ways to laugh, maybe cry this semester as you're navigating some of these tough classes like Gen Chem. So what we're going to be doing is we're going to start with empirical formulas. I had a lot of requests this week just to discuss like this process. So that's where we're going to start talking about chocolate. Everyone's favorite compound is theobromine in chocolate. So we're going to be looking at that first. But again, the goal of this session is just it's going to be catered to whatever you are working on in chem right now. So whether that's acid-base chemistry or balancing reactions, put your questions in the chat and I will answer them. And we are here for 1 hour. All right. So without me continuing to talk at the camera, let's go ahead and just jump into empirical formulas. So I have this practice problem already written out here. We have the active ingredient in chocolate is theobromine. If the sample contained the following percent composition, what is its empirical formula? So with this, I do have like a little rhyme to help you remember this process. So what you want to remember, and just bear with me for a second while I write this out. It's like a little rhyme. So you want to remember percent to mass, mass to mole, and I will go through each of these steps. Divide by small, multiply till whole. All right, so if you can get this rhyme in your head, you're going to feel like this is such a simple process. So let me go ahead and walk you through this. So first step, and this is a step that everyone forgets. If you're given all of these percentages of these different elements, right, we're going to assume that we have a sample that has a mass of 100 grams, in which case I can literally take that percentage sign and change it into a gram. So that means that this sample would have 46.6 grams of carbon, 4.8 grams of hydrogen. You get the point, right? So we're literally just taking that first step is just changing that percentage sign into a gram, and 30.8 grams of nitrogen. All right, step one, done. Next step, mass to mole. If we want to make comparisons between two different elements, we can't do that on a grams to grams basis. We have to convert all of those into moles. So now what I'm going to do is just divide by that molar mass that you find on the periodic table for each of these. And your periodic table might be slightly different from mine. And that's okay. Just use the numbers that you're given. All right. So I'm just taking each of these. I'm dividing by the molar mass to convert from mass, from grams, into moles. I need to just quickly do that. So 46.6 divided by 12.011. And with this, it's going to seem really tedious, but you want to carry out as many decimal places as you feel comfortable writing down. Because when we get to that next step where we're comparing each of these elements to the others, the more exact we are with the moles, the better our numbers are going to be. Just the cleaner our numbers are going to be. Because again, the goal with this is to get that to that empirical formula, right, where we have whole number ratio between each of these elements. All right, sorry, let me just go ahead and divide this out. You can hear me cranking away at my calculator. So with this live, my goal is for you to be sitting down with the periodic table, with a calculator, and trying out these problems yourself. These sessions and in chemistry, as you've probably learned, active studying is going to be the best way to approach this course. So the more that you can write down and actually actively engage with in this session, the more beneficial it's going to be for you. And it looks like the questions are coming in, so that's great. All right, so let me just go ahead and put all of this down. 198, 429. All right. So we have done the first two steps. Step one, we converted all of our percentages to masses, assuming that we had a total sample of 100 grams. Then we converted from mass to moles. We divided by the molar mass of each of these. Now we're going to divide all of these quantities by the smallest quantity. Again, the goal is to get to a whole number ratio for our formula. So we're going to pull out this number, and that's what we're going to divide everything by. So I'll just say divide by. Okay, so as we do this, we're going to get those whole number ratios. So we know 1.1125 divided by that means we'll have 1 atom of oxygen. We're going to have about 2 atoms of nitrogen. We're going to have about, what is that? We're going to have about 3.5 atoms of carbon and then 4 atoms of hydrogen. So now I would help if I actually wrote out 3.5, right? So now what we're going to do is we've done that third step. We've divided each of these quantities by the smallest number. Now we want to multiply until we get to that whole number. So looking at carbon, unfortunately, we can't have 3.5 carbon, right? You can't have C 3.5 H4. So instead, what we're going to do is we're going to multiply each of these quantities by 2 to get to our whole number. So we're going to just multiply everything times 2, and that gives us our empirical formula of, let's see, sorry, C7H8 O2N4. All right, so that is the process of finding an empirical formula. If you're asked to take this one step further and find that molecular formula, you'll be given a molar mass. All you have to do is find the molar mass of that empirical formula. Take the molar mass of the empirical formula, compare that to the molar mass of the molecular or the actual formula, and that will tell you how many times you need to multiply the empirical formula to get to the molecular or actual formula. There are a lot of cases where they're going to be exactly the same, and that's okay too. So you can always just use this to double check your work. All right, so this was just a quick review of empirical formulas. This is the process. Again, screenshot this. If you don't have this little rhyme in your head, this is the easiest way to navigate this. And if you take it one step further, you do a combustion analysis or anything like that, you just have to make sure that you're figuring out your masses of carbon, masses of oxygen from the carbon dioxide and the water that you're given. All right, let me jump into the chat and see what questions you have. This is just a live office hour brought to you by Chegg. We are here weekly, and it's not just Gen Chem. There are 11 different live sessions that Chegg is hosting. So helpful for all of you, especially as you start having those first exams of the semester. So let's go ahead. Let me jump into the chat and see what else we have tonight. Okay, it looks like resonance structures. I have a request for Vesper theory. All right, let's go ahead and do resonance structures, and then we'll talk about Vesper, and then we'll go from there. All right, so let's talk resonance. And with resonance, we have to talk formal charge. All right, so if you think of something that resonates, think it from like a musical perspective, right? If you have a string that is resonating, it's moving back and forth. With a resonance structure, we're going to have multiple structures that are possible for a covalent molecule. So let's say I have thiocyanate. It's one of our polyatomic ions. If you have not memorized the polyatomic ions, this is a helpful one to know, but it's just SCN. It has a charge of -1. So what we want to do first is draw the possible Lewis structures. All right, so with this, we're going to put carbon in the middle. Let's go ahead and calculate our total number of electrons we have to worry about. But with this, you can kind of guess and check. So I'm going to put carbon in the middle. I'm going to put nitrogen and sulfur on either side of that. So thinking about this right away, I'm going to look at this and say, okay, I'm going to need some double bonds, maybe a triple bond on one side. And that's how I'm going to draw these different resonance structures. So looking at this, let's do double, double. We'll end up with 2 lone pairs on each of these. So that is one possibility. Another possibility would be a triple bond to sulfur, and then a single bond to nitrogen. So I'm just filling in those lone pairs. And then our third resonance structure, our third possibility is the opposite. So let's draw a triple bond to nitrogen. All right, so each of these has thiocyanate -1 charge. How do I determine which one is the most likely structure? And with this is where formal charge comes into play. So formal charge is just going to help us designate the best structure. So basically, we're going to look at the charge of each atom in this compound and decide what's most likely. So let me just write out the formal charge formula. So it's always going to be equal to the valence electrons minus the dots minus the sticks. And you're like, Corinne, that is not a normal formula. What are you talking about? The dots refer to the lone pairs, and then the sticks are the bonds. So the bonded electrons divided by 2. All right. I think it's a lot easier to remember dots minus sticks, so that's the way I teach it. All right, so let's just go ahead and look at the formal charges of these. So looking at sulfur, sulfur has 6 valence. So we'll do 6. It has 4 dots and 2 sticks. That's going to have a charge of 0. Carbon has 4 valence, no dots, and 4 sticks. That gives us also a charge of 0. And then nitrogen has 5 valence minus 4 minus 2. That has a -1 charge. But if we add all of that up together, the overall ion has a charge of -1. So something's going to have a charge other than 0. So ideally with formal charge, you want to be as close to 0 as possible. You also want to make sure that anything that has a negative charge is the most electronegative atom in the compound. So let's just skip over and look at the other structures. So looking at sulfur again, same thing. We can just go ahead and fill all of these in. And hopefully, how about you work on that third structure while I'm filling in this one, so you get that practice with it. All right, so looking at these three structures based on formal charge, we want the numbers to be the smallest magnitude, right? We want it to be as close to 0 as possible. So right away, we know this one is not going to be the case. We have a +1 on one side and a -2 on the other. That's not going to be our best structure. So then it's between the first and the third structures. And really the only difference here is where that negative formal charge ends up. So with the first structure, that is on nitrogen, versus on the third structure, it is placed on sulfur. Because nitrogen is going to be more electronegative, it makes more sense for nitrogen to carry that -1 charge. So therefore, this would be our preferred structure. All right, so just a little bit on resonance and formal charge. Again, let me hop into the chat and see what else you need help with. Looks like we have quite a bit of questions related to acid-base chemistry as well. We can definitely look through those too. All right, so this is just a weekly office hour brought to you by Chegg. This is my first time doing it on a whiteboard. This is actually how I tutor, though, so I don't mind doing it this way, but give us some feedback. If you don't like seeing it this way, if you'd rather see me at my actual whiteboard, let me know and we'll switch it up next week. All right, so we're going to move forward into acid-base chemistry unless any other questions or requests come in from the chat. Yeah, okay. So it looks like we have something from TikTok. Can you explain molecular geometry and Vesper theory? Absolutely. All right, so now we're going to switch gears. We just did resonance and formal charge. We're going to switch gears and just do some molecular geometry. And I have structures somewhere here in my basement. I should have had those ready for you because it's so much easier to see this. All right, so let's talk Vesper theory. This is one of those weird things in chemistry, right? Like, why? Oh, thank you. My iPad just decided to talk to me. It's one of those weird things in chemistry. Vesper. Why do we call it Vesper? It should be Vesper, right? So valence shell electron pair repulsion theory. It's basically this idea that the electrons are going to repel each other. So, right, electrons are negatively charged. If I have two negatively charged electrons, they're going to want to be as far from each other as possible. So that's what this whole theory is based on. And what we're going to use is we're going to use the Lewis dot structures. We're going to see the number of bonded atoms and non-bonding or lone pairs on that central atom, and that's going to determine the shape of the molecule. How much is going on that central atom, because that's going to determine how everything's going to spread apart. All right, so let's go ahead and look at this. All right, so let's say we just have ammonia and H3. If I were to draw the Lewis dot structure of ammonia, we have nitrogen in the center with 3 atoms of hydrogen bonded to it. Nitrogen is also going to have a lone pair on top of that. So now when we look at this, this has 3 bonded domains plus 1 non-bonding domain. Believe it or not, this lone pair on top of nitrogen actually takes up more space than a bond does. So basically what's going to happen is all of these things are going to spread out as far from each other as possible, leading to this shape that we call trigonal pyramidal. So we're going to have nitrogen in the center. We're going to have hydrogen kind of creating a pyramid with one coming out towards you. If you see this, if you see like the lines, the dashed lines, the whole goal is just to show the 3D shape. All right, so you're trying to show that there's something coming out towards you, there's something going behind you, and then there's something in that plane. And then what I didn't draw in, right, are those electrons on top. So those electrons are taking up space on top. That's what's causing this to bend into this pyramidal shape. So we call this trigonal pyramidal. So basically with geometry, what you have to do is you have to get a lot of practice drawing those Lewis dot structures, because everything is based on what's going on in the central atom. If your peripheral or your outer atoms have 6 electrons on them, it doesn't matter. Okay, those are not going to change the shape of the molecule. And I'll draw an example of that. So let's say I had carbon tetrachloride. So again, I have carbon in the middle. We're going to have 4 atoms of chlorine. The prefix tetra means 4, and then each of these chlorine atoms is going to have 6 electrons around it. Okay, so now looking at this, I have 4 bonds. This is going to form what's called tetrahedral geometry. So I have the carbon in the middle, I have chlorine on top, and then I still have that same kind of pyramid-like structure, a tripod basically on the bottom with each of those chlorine atoms. So again, this is known as tetrahedral. The prefix tetra, right, tells you we have 4 bonds to that. So it gets a lot more complicated from that. Let me know if you'd like to see up to octahedral. I'm happy to go through the expanded octet and whatnot. But basically with Vesper theory or with geometry, get really comfortable with drawing out those Lewis dot structures so you can then translate that into the 3D shape. And I'd recommend just making, like on paper, take the time to actually write out an example of each and then show what that looks like. So if I have 2 bonds and then 2 lone pairs, that leads to bent geometry. Versus if I have just 3 bonds and no lone pairs, that's trigonal. That's just the trigonal. I can't even think of the name now. That's crazy. That's the power of like being live. You forget silly things. But I'm gonna have to write that down at some point during this when it comes back to me. But just take the time to actually write out all of those so that you have that in front of you and you can practice. So you recognize each of those and you can keep moving from there. All right. So let's see if there's anything else on there. Yeah, okay, awesome. Sorry, I guess I've missed a lot of questions on the chat. And someone help me out if you can remember what the name of this, like why can't I think of that right now? I'm just having a little, my brain is not working right. So let me remind me of what the trigonal the other geometry is. This is crazy. I've been doing this for decades and I can't remember that right now. What's the best way to memorize all the angles and shapes? That's a great question. So it looks like that one came in from YouTube. The best way to memorize them, and unfortunately, there aren't too many things you have to memorize in chemistry, but just taking the time to draw out a diagram, right, with examples of each, count the lone pairs, and then just memorize it. The more you're exposed to it, then really there aren't too many. Even if you're doing the expanded octet, right, you only have like 8 conformations to remember, and just practice with that. For most classes, you don't really have to know the bond angles. If you are stuck and you can't remember the bond angles, you can actually divide 360 and then look at that, right? So it's trigonal planar, by the way. If you're doing something that has trigonal planar geometry, for example, so BH3, I'm glad that came to me. I don't know why I could not remember that. So this would be an example of trigonal planar geometry. So you don't have a lone pair on that central atom. Everything is just going to spread as far away from each other as possible in 360 degrees. 360 divided by 3 tells you each of these is going to be 120 degrees apart. So there are ways to reason your way through it if you don't have those angles memorized, but hopefully for your course, you don't even have to have those memorized. All right, let's see. Yes, thank you. And it looks like Rocco C saved me too on YouTube. Thank you for that. All right, so guys, these are just live office hours. My goal is to help as many students as possible. We're going to jump all around. It's just a Gen Chem themed office hour. If you are here for Orgo, know that we have an office hour with Professor Dave tomorrow night. But the plan is just Gen Chem. So let me know what else you'd like to review. I'm going to jump back into the chat and see. Yeah, and someone just had a generic question. How long is this for? Yeah, so this session is 1 hour long. And then Chegg has 11 of these hour-long office hours all week long. So check them out. You can find them on YouTube, TikTok, Instagram. It looks like we've had a couple questions coming in from each of those feeds. So hopefully it looks good on there. It looks like okay, what's your advice for Gen Chem 2? Yeah, Gen Chem 2. So with Gen Chem 2, you're going to be getting into solution chemistry and acid-base chemistry. The more practice problems you can complete, the easier it's going to be. And take the time to memorize those polyatomic ions. Take the time to ask questions and go to your office hours in person too. It makes a big difference if you get that FaceTime with your professors and with your TAs. But if you've made it through Gen Chem 1 and you're doing well, you're going to be okay in Gen Chem 2. It's Orgo that's going to be tough. All right, let's see. Let's keep moving. So let's see. Okay, I had a question on here, just how to identify endothermic changes. So this one's coming in from YouTube. How do I know something that is endothermic? So chemistry, one of the most frustrating things about chemistry is all of the terminology, right? But the good thing about it is you can break down most of these complicated words to kind of get hints as to what the heck that term is talking about, right? So if we look at the word endothermic, endo means within. Okay, thermic, probably know thermo, right? Thermochemistry, we're looking at heat. So basically, an endothermic system is something that absorbs heat. So basically what's going to happen if you're looking to identify an endothermic reaction, it's actually going to feel colder after the reaction, which is confusing. So if you have like a cold pack that you've used for sports where you've had to break it and shake it up, it gets really cold. That is an endothermic reaction. The reason it feels cold is because it's taking that heat in from the surroundings. So if you are looking at a reaction profile, so let's say you have something like this and you want to figure out whether it's endo or exothermic, this would represent an endothermic reaction. So you're looking for the change. This would be your enthalpy, right? The change in energy between your reactants and your products. Because the energy of the products is higher than that of the reactants, this would be an endothermic reaction. Okay, that would be endo versus exo. I can just quickly draw that as well. Exo, you're releasing heat to the surroundings, right? So in an exothermic, think about an exoskeleton, right? Outer skeleton. You're releasing that heat. The energy of the products is going to be a lot lower than that of the reactants. All right, so just quick little tidbit on just endo versus exo. And I'm excited to hear this is your first time seeing Chegg live. Chegg is here live for 11 hours a week right now, because Chegg really is they really want to help as many students as possible, which is why I love working with Chegg. I'm so excited to be here. We're doing weekly Gen Chem office hours a couple times a week. You can also join for Orgo tomorrow, and then there are all kinds of math and all kinds of other office hours. Yeah, so okay. How can I tell? Okay, so from Instagram, how do we tell what's been oxidized and what's reduced in a redox reaction? Um, yeah, so let's go ahead and talk about that. So we'll do a little bit of redox. So what I love about these office hours is we are jumping all over the place. So stick around. We are here for another 35 minutes. I will hit as many topics related to Gen Chem as possible. Keep asking those questions and I'll try to keep going through them. And whatever I don't get to this week, I will save and I will plan on getting back to those next week. All right, so redox. All right, so with redox, a lot of this is going to be counterintuitive. How do we tell what's been oxidized and what's been reduced? So you've probably heard the mnemonic device, right? Oil rig, which basically is just oxidation is the loss of electrons, reduction is gain. And let me see if I have like a redox reaction written anywhere. So I can just go through that. Give me 1 second to pull up a redox reaction and we'll go through an example as we're doing this. Um, I wish I had like perfect examples in my head all the time, right? But because we hit on so many different topics, it's good to have reactions that are going to work out. Because when I make them up on the spot, they don't always work out so great. All right. So let's say we just had a simple half reaction. Yeah, let's just do that. All right. So let's say I have V2O3 going to VO. And we want to figure out whether this is an oxidation or reduction. So with a redox reaction, please be aware that you're going to have both, right? Because it's all about the transfer of electrons. But in this example, I just want you to practice identifying what's going on. So with this, I like to just draw, this is what my teacher had me do in high school years ago, many actually decades ago. But I think it's the easiest and cleanest way to keep track of this. So if I look at this, we're looking at vanadium oxide here. So vanadium 2 oxide, my product, oxygen has to have a charge of -2. That means vanadium is going to be +2. So I'm just trying to keep track of that. Versus V2O3, I have 3 atoms of oxygen that has a charge of -6. That means that vanadium in this case, -6 divided by 2, that tells me that this has to be +3. So what has gone on now for vanadium to switch from +3 to +2? And this is where it gets counterintuitive. If your charge has decreased by 1, it's because you have added a negatively charged electron. All right. So that's you got to think like if you add something more, if you had something negative, if something negative happens to you during a day, how are you going to feel? You're going to be more negative, right? So you're adding a negatively charged electron that's going to decrease the charge of vanadium in this case. So now going back to that mnemonic device, okay, oxidation is loss, reduction is gain. So in this case, vanadium is going to be reduced because it has gained an electron. So just a quick, that's how we can tell what's being oxidized versus what's being reduced. If you are looking at an electrochemical cell, there are a lot of other ways to also identify that, and I'd be happy to get into that. Please just let me know. I'm going to jump back into the chat, see what other topics we can hit on tonight. But if you'd like more with that, please just let me know. That's the beauty of these sessions. Like it is really supposed to be just an office hour, right? And if you were going to an office hour with your TA, right, everyone would be studying the same exact thing. Which is super convenient for an office hour, right? But this one, we're just hitting anything related to Gen Chem. So keep putting those questions in the chat. Like I said, if I can't answer them all, I am happy to save some for next week. Okay, let's see. Yeah, so someone asked about stereochem. So stereochem, you'll be doing, so Orgo is tomorrow night. So just so you know, there are um, tons of different office hours. A lot of them are like for first or second year classes. So this one again is just for Gen Chem. Yeah, all right, here. Sorry. It's taking me a while. You guys are putting such great questions in the chat. Please keep that up. We have another half an hour. I'd love to hit as many topics as possible. All right, let's do something a little bit more complicated. So let's do an example of an equilibrium question. So we'll do a rice table with that. So we're going to do, this is a question from from YouTube, can you show an example for ice problems at equilibrium? Absolutely. And I think I have a tough one prepped too. How many of you are doing acid-base chemistry right now? I feel like we should do that, right? Like it's that time of year where everyone is struggling with acid-base chemistry. If you are, please put an emoji in the chat. We've all been there, right? All right, let's do. Let me write out this example, and then we'll keep moving. All right. So, what are the equilibrium concentrations? And like I said, the best way to get something out of these live sessions is to grab a piece of paper, grab a periodic table and your calculator right now. So you're not just listening and watching me do this. Because after I work through this problem, it's going to go in one year and write out the next. You need to actually write it down. So you're making those connections and you remember how to do some of these tricky processes. All right. So what are the equilibrium concentrations? And also call me out if you can't read my handwriting. I know I'm normally at a whiteboard. So typically this is a little bit cleaner than on my whiteboard, but let me know if you can't read anything too, and I'd be happy to try to figure that out. All right, so we're trying to find the equilibrium concentrations of a 0.15 molar HF hydrofluoric acid solution. So quick trivia question, is HF a strong acid? What do you think? Um, so go ahead and put that in the chat. Is HF a strong acid or not? Um, you see all kinds of videos with hydrofluoric acid where it's like eating through chicken bones and things like that, but it is not actually classified as a strong acid because strong acids have to completely ionize in solution. HF does not do that. Therefore, even though it is a dangerous acid, it is not classified from a chemical perspective as a strong acid. So definitely know that distinction. I think I had a lot of questions this week, like basics of acid-base chemistry. That's the one. If it is classified as a strong acid, it's because it completely ionizes in solution. All right, so what we want to do is we want to figure out the equilibrium concentration. So if you see something like that, you know you're going to have to use that Rice table. All right, so first thing we need is the dissociation reaction. So let's say I have HF. It's going to separate or ionize into H plus and F minus. I should include the states here. Everything's going to be aqueous. If you have a liquid or a solid, remember you do not include those with Kc, any of your equilibrium expressions. All right, so that's my reaction. I'm gonna look at my initial, my change, and my equilibrium. Again, I like to use the Rice table instead of ice because then you can just have the reaction at the top, and it just makes it easier to keep track of everything that's going on. All right, so initial, what do we know, right? We know that we have a concentration of 0.15 molar. We're going to assume we don't have any of these ions in solution. We have no indication that this was done in a common ion kind of situation, right? We're not doing this in a solution of sodium fluoride, anything like that that would give us any of those other ions. So initial concentrations are going to be assumed to be 0 for those two products. All right, so what's going to happen? We're going to subtract X from HF. We're going to add X to each of these. This is a really simple one because it happens to be a 1-to-1 ratio. So you're just adding plus x. If I had a coefficient of 2, then I'd be adding 2x here. So just know that that's how this table is going to change just based on the stoichiometric coefficients or the coefficients from that balanced equation. All right, so now what's going on at equilibrium? Because that's our whole goal with this, right? So I have 0.15 minus x and plus x plus x. Not as intimidating as you'd think, right? Like the Rice table is really not as bad as everyone says it is if you just practice with it. So now the hard part, right, is translating whatever we just did into what the problem's asking for. So we know we have our Kc value, and that's equivalent to 1.58 times 10 to the minus fifth. Did I forget units with that? No. So with any of those equilibrium expressions, you do not have units attached to those. It's like the one case in all of chemistry where you don't need a unit with that answer. So Kc, Kp, or Ksp, you don't need those units. All right, so we're just going to set that up, right? So I want to set that up. I'm going to have my concentration of my products over my reactant. Again, if I had a solid or a pure liquid like water, in there, it would not be included, but because all of these are just aqueous solutions, I am going to go ahead and put all of that in there. So I am going to go ahead and use the 5% rule. So basically, I'm going to assume that this is such a small amount that it's less than 5%, and I can just ignore X. And that just makes the algebra a little bit easier. While STEM can't like get mad at me for this, everyone in chemistry does this. So rather than having to use the quadratic formula for something like this, you can just negate X. So what does that mean? I'm going to have X times X, or X squared, over 0.15 equals my 1.58 times 10 to the minus fifth. So now all I have to do is multiply both sides by that 0.15, solve for X, and then that gives me my equilibrium concentration of both H plus and F minus. So what would that be? X would be equal to 0.0, it's really small, 0.00154 molar. If you were paranoid about the 5% rule, you can then run that back in, right? So use the percent ionization. Compare your H plus compared to your HF concentration. If I look at my H plus, 0.0015 molar compared to 0.15, that's a 1.2%. So it is small enough that we can ignore X, and that's going to be the case, I'd say 9 times out of 10 with these types of questions. All right, so that was just a quick review of equilibrium with a rice table, a little bit of acid-base chemistry, a little bit of review of that. Let me hop back into the chat, see what else you need help with tonight. Oh, Jeeves, that hurts my heart. You said chem sucks. Obviously, I believe differently, right? Yeah, so on Instagram, can you share a list of units for all of the different things such as kilojoules, moles, joules, and other ones? Yeah, I could go through like the main units. Actually, sorry, I just saw another question on TikTok. How do I know which side to add or subtract X to? So basically what we're doing is we're looking at what's happening in this reaction. So so initially I had just HF in solution. So I started out with just this, right? And my concentration was 0.15 molar. As the reaction proceeded, right, I'm going to lose some of that, and what's going to happen is I'm going to gain these two products. So basically what you're doing is you're saying, okay, as the reaction proceeds, I'm going to expect it to shift towards the product side. So that's why you're just going to subtract X from, so we don't know how much X we're losing, right? We don't know how much is ionizing yet. But then we can use like the Kc to figure that out. We could also work backwards. We could figure out what was going on with each of those, right? We have X. We could then substitute that back in. So basically, you're just looking at this reaction. You're imagining it happening in solution. So I have HF. I'm watching it ionize or separate out into H plus and F minus. So that's how I know whether I'm subtracting X and where I'm adding it. It's always going to be the same, right? Like, so you're going to be subtracting from your reactants and adding to your products as that reaction proceeds. The only change, again, would be if you had a coefficient. So let's say I had 2F here, then I would make sure that I'm adding 2X to that one. So that's just kind of how that could change. All right, thankfully we didn't have to do that for this problem because it was just a 1-to-1 ratio, but that's kind of how you do that. And honestly, with these, the more you practice with these tables, the easier it's going to feel, the more natural it's going to feel. Each problem, yeah, is going to be slightly different. And let's say I had a common ion. So let's say instead this was happening in a, I don't know, so we'll just say reaction is proceeding in, I don't know, 0.10 molar sodium fluoride. How would that change these numbers? So now we have HF in solution with NaF. We're going to assume that that means we have 0.10 molar fluorine. All right, so that's how this would change a little bit. So then I would have the 0.10 plus X would be my concentration at equilibrium, right? So this would be 0.10 plus X. And then when I go to substitute that in, that changes this. It's going to change your numbers slightly. So note there are slightly different ways for this to change. Yeah, so is ice only for these types of reactions? Yes, so when you are looking at equilibrium concentrations, when you're looking at acid-base reactions, or acid-base titrations, that's where you're going to see these rice tables. Again, I prefer using rice over ice. So you're going to have the reaction first. You're going to have your initial concentrations, the change until you get to equilibrium, and then your equilibrium concentrations. Um, yeah, and then okay, there's another question related to this too. So coming in from Instagram, can you explain half equivalence points in relation to acid-base chemistry? Yeah, let's roll into acid-base chemistry because I know that's been a hot topic lately, as a lot of students are getting into that right now. So let's just like do a quick acid-base. Like let's do the I don't know some of the basics of acid-base chemistry. Um, all right, so I guess a good question would be like, can you explain what you can find on like an acid base titration curve? Like, how do we interpret that? What can we pull from that? And it's great that you've noticed, like, how do you explain half equivalence point? So let me just I'm going to draw out a titration curve. We'll do, so I think that's going to help you all see this, like, it's a good hack, right? You remember something happens at the half equivalence point. What's going on? So in Chem 1, right, in high school Chem, it's really easy. Do everything with strong acids and strong bases. And your equivalence point happens right at a pH of 7. It's a perfect neutralization. Super easy. You might still miss your you might still miss your endpoint with your titration and whatnot, but like the math, it's so easy. And then you get into Gen Chem and AP Chem, and all of a sudden you're doing weak acid, strong base titrations, or the opposite, right? Um, Weak base, strong acid titrations, and it's not as straightforward. So let's look at a titration curve, and then we'll talk about that half equivalence point as we're looking at that. All right, so I'm just going to draw a curve. Let's see. Don't judge me. That's not too bad, right? That's not bad. All right, so with this, we have somewhat of a low pH. So this is my pH of analyte. Or this is going to be my volume. All right, and if we're thinking about the titration, right, like what's actually happening, we have our analyte in an Erlenmeyer flask underneath our burette. The burette has a strong base. We're slowly adding that to it. We're mixing it. We're using some kind of indicator. When that changes color, we know that our titration is past that endpoint, right? And then we can stop adding the base in this case. So what can we find out about this? So we have certain regions that we need to be aware of. Let's see, let's say this is 7. So this is what we call the buffer zone. And I did have some requests for buffers. So if you want some help with buffers, I do have a good sample question ready. And I'm happy to go through that as well. All right, so at the buffer zone, we're going to have what's called the half equivalence point. And at this half equivalence point, something magical happens. Basically, you're going to have half of your acid is neutralized. So what does that mean? You're like, Corinne, you're getting kind of crazy here with all of this. So basically, this means that your weak acid is equal to your conjugate base. Okay, and the cool part about this, your pH is equivalent to your pKa at that half equivalence point. All right, so basically it's a spot where you have neutralized half of your acid, whatever that acid happens to be, and your moles of weak acid are equivalent to the moles of weak base. So that's why your pH is equal to the pKa, and if you're using the equation where you're trying to solve for the pH of the solution, it makes it really easy to do that. Versus your equivalence point, right, that's where you have essentially neutralized all of your acid. And that's where you have reached this point, right, where you have equal moles of your acid and base. So with this case, with a weak acid strong base titration, that's going to be slightly above 7 because we have a strong base that we're adding. If we're looking at a strong base, weak base strong acid titration, it'll be slightly below 7. So with a strong acid strong base, you'd expect the equivalence point to be right at 7. With these weak titrations, it's not going to be the case. It's based on whatever has the strong part, right, is going to kind of pull the pH in that direction. All right, so basically that's what you can pull from a titration curve. I hope that helps with the pH. So knowing that the pH is equal to the pKa at at the half equivalence point is really helpful when you're doing some of those equilibrium calculations and some of these acid-base calculations. Yeah. All right, so let me go ahead. I'm going to jump into buffers as well. And I promise I'm not forgetting about the question on list of units. So let's talk buffers a little bit because that relates really well to this, and then we can see how that can be really helpful. That little hack, right? The pH equals the pKa. All right, all right, buffers. Let's see. I know I have that practice problem. Okay, so I'm just going to run through a buffer problem. This is going to help with everyone who's working through acid-base chemistry right now, because this is one of those things that everyone seems to struggle with because it's really intimidating at first, but it's another one of those cases where, just like when you did your first rice table, you did the first table, you're like, what is this? This does not look like anything I've done in chemistry. But then after you practice with it, the more you practice with it, the more confident you'll feel. And Chegg is here to support you. So, as I've said, like, this is not the only office hour. There are 11 of these weekly office hours, and there's even another Gen Chem one on Thursday nights. So please keep coming with all those questions, and we are here to help you. That's the goal of these sessions. All right, so we have a buffer. 1 molar acetic acid. I'm just going to shorten this. 1 molar sodium acetate, so NaC2H3. O2, one of my biggest tips is you actually should memorize those polyatomic ions. I like chemistry more than bio because I don't like memorizing things, but you should know those polyatomic ions. All right, so let's see. What is its pH if the Ka of acetic acid is, let's see, 1.77 times 10 to the negative fifth? All right, so with a buffer problem, what is happening with a buffer? Let's back up. Let's say you have a question, you're asked to pick out a buffer system. So a buffer is basically a system that's going to resist changes in pH up to a certain point. So what we call the buffer capacity. So it's going to be a weak acid and its conjugate base, or a weak base and its conjugate acid. It's going to be a conjugate acid base pair. If you need help with those, please ask. Yeah, and Evan, it looks like you just asked a question on YouTube. Please do. Please keep putting those questions in the chat, and I will see those and answer them as quickly as I can. All right, so with this, so basically a buffer, you have to know that buffer system can never contain a strong acid or a strong base. So if you're asked to pick out a system, you're looking for a weak acid and its conjugate base, or a weak base and its conjugate acid. So that's how we kind of pick those out. So acetic acid is going to be a weak base. When acetic acid loses that H, it becomes just acetate, right? And then we'd have, that's sodium acetate is its conjugate base. All right, so what is its pH going to be? So the easiest way to look at this one is knowing that the pKa is going to be equal to the negative log of Ka. And I feel like I saw a question in the chat earlier tonight asking, like, how do I memorize all of these questions? So how do I memorize everything with pH and all of that? There are patterns to it. There are patterns to everything in chemistry. This is one of them, right? pH is equal to the negative log of H plus. This one looks really familiar, right? pKa is the negative log of Ka. So I'm just going to take the negative log of our value, which was given, times 10 to the negative fifth. Let's say you're not given that Ka value. You can find those in the appendix of any of your textbooks. You can also find those online, and those values are standard. So they're standardized. So you should be able to find a pretty accurate number if you need that Ka value. All right, so that's going to be equal to 4.752. Is my pKa. All right, and something I have not been talking about is sig figs. I apologize. So with sig figs, you're always going to base the number of sig figs on your least precise number given in the problem. In this case, I have 3 sig figs for each of these values, so my final answer should also have 3. It's okay to carry more than 3 sig figs as you're doing a problem. I always tell my students, write down however many decimals you want to from your calculator, and then go back in and round for sig figs. It General rule of thumb, 3 sig figs is a safe bet. All right, so far I have solved for my pKa, but that doesn't really help me because I'm trying to find my pH. So this is where you need to remember the Henderson-Hasselbalch equation, right? Which is just going to be pH equals the pKa. Um, so let me go ahead and write that out for you. It's the pKa minus the log of your base, which we'd say is our A minus, our conjugate base, divided by the concentration of our weak acid. This can be flipped, right? If you're dealing with a weak base, it will be its conjugate acid on top. All right, so now it's just a matter of substituting everything in. We are given our concentrations. So this one's really easy. We just have to plug those values in. So pH is going to be equal to 4.752. That was my pKa value that I already calculated, minus the log of 1 over 1, kind of boring. That's just going to be equal to 1. Therefore, my pH equals 4.752. Again, if we round that based on sig figs, we just want to have 3 sig figs based on what everything else that we're given in that initial problem. So this would end up being 4.75 as our pH. So we'd say this is the half equivalence point, right? Because our pH is equal to our pKa. We could shift this slightly, though. Let's say instead we wanted to change this up. Here, let's see. Let's switch this just to a different concentration. So let's reduce the concentration of conjugate base. Okay, so if I do this, that doesn't change my pKa value. But now what is going to change, right, is what's going on here. So this now, my log, it's going to be 0.80 over 1. Sorry, let me put that in my calculator. So 4.752 minus our new log will now give us a value of 4.655. So we'd say that's 4.66 is our new pH. All right, so if our concentration of conjugate base is not as high, we're going to have a lower pH, right? Because we are not at that half equivalence point. We still have more of our weak acid in solution compared to our conjugate base. All right, so that was just a quick buffer problem. And then let me check the chat and see what else. So we've done a little bit of everything. And Evan, yeah, okay, resonance. Yeah, we totally talked about resonance earlier in the session. So the cool thing about these sessions, now that we're on YouTube and we're trying out this new platform, is you will have access to all of the sessions. So everything is posted on Chegg's YouTube. So if you're not following them yet, please follow them so you can jump back in. If you hear me say, oh, I already did that. I did that earlier in the session. You can go back to that feed and watch that. But I'm happy to, yeah. You're technically in Orgo right now. Yeah, so we'll keep going through some of the basics. So resonance basically is just this idea that we have different possible Lewis structures. So we looked at, for example, thiocyanate. So SCN minus, and I'm just going to draw 2 of the structures. We'll draw the 2 best structures. I think I'm going to have to try to remember it now. All right. So let's say I had these 2 resonance structures. So resonance just means, think about the word resonate. Something is moving back and forth. We have the movement of electrons. I guess ozone is a really good example of resonance, right? Ozone is O3. Right? And we're moving double bonds around. It's where you have multiple options with those Lewis dot structures. I didn't actually draw the full Lewis structure there. Don't judge me. But basically, this is the idea that we have several possible structures. And what you have to do is you have to look at these structures. You have to determine the formal charge at each atom and see which one is most likely. So with formal charges, you want the values to be as close to 0 as possible. And then you want your most electronegative atom to carry the negative charge. So in this case, when we did that, we found out nitrogen has a formal charge of -1 here versus sulfur has a formal charge of -1 here. Because nitrogen is more electronegative, this would be our favorable structure. So it's just that process of looking at the different possibilities and then using formal charges to figure out which one is most likely. And yeah, the goal of this session is just to go through any and every topic from Gen Chem. We did resonance, we did empirical formulas, we've done acid-base chemistry, equilibrium. We've done a little bit of everything tonight. We did some molecular geometry. I feel badly. I need to go back to that list of units from Instagram. We can go through some common units. So we had a question earlier, can you share a list of units for all the different things in chemistry? Yeah, there are so many different units. I'm going to write down some of the most common units, the ones that you will see the most, right? So we have the mole. Um, I, I, I don't know. We have kilojoules. There's so many units. I guess let me switch gears. So as a teacher, I don't gatekeep. I'm a teacher who enjoys making it so as many people can understand chemistry as possible. The easiest way to survive chemistry, if you're struggling with units, or let's say you're doing gas law problems, use your constants. So let's look at the gas constant, for example. All right, so ideal gas constant. We have different versions of this constant, right, to make these relationships work based on whatever units you're working with. So let's say I have 0.08206 per mole Kelvin. Okay, versus these are just two different versions of this constant. If you are doing a problem and your pressure is not in atmospheres, you're given a pressure in kilopascals, you're given a pressure in torr, you need to make sure that everything matches your constant. Okay, so when you are doing these complicated questions where you have lots of different variables that you're working with, lots of different quantities, always make sure that your units match whatever that constant is. If you're looking at specific heat, are you looking at joules per grams degrees Celsius or joules per grams Kelvin? Make sure you are checking your constants that are included in those equations to make sure that every other value matches up with that. It is always worth the time to actually write out those units as you're doing those questions, because it's such a good way to keep yourself from making a silly mistake too. So just a little like chem hack is always check out your constants in your constant sheet, because that will give you a good idea of what you're looking at. And let's say like you're doing gas law problems and you don't know whether to use the ideal gas law or the combined gas law, right? Look at your units, see what your count how many different species you're working with, right? Looking at those, are you looking at a change in a system, or are you looking just at the system in one moment of time? So there are always tricks to trying to figure out how to navigate those wordy problems. Let me see. Sorry. Let's see. Thank you all for being here. Thank you for asking questions. Let's see if there are any others tonight. So we're going to be here again next week. Also, let me give us some feedback. This is my first time writing on a notebook like this instead of being up at my whiteboard. If you prefer the whiteboard, let us know in the chat and I will switch it back up next week. But we're here at the same place, same time next week. Let's see. Yeah, all right. How to identify conjugate acid base pairs? We'll end with that. We have just a few minutes left. And guys, if you still have questions, if you have burning questions, remember Chegg is going to be here again with another Gen Chem office hour on Thursday. Also, put your questions in the chat and I will save them so that we can start there next week. So let's just identify conjugate acid base pairs. So with acid-base chemistry, we looked at a couple of reactions related to acid-base chemistry. We looked at hydrofluoric acid. The best thing that you can do is just imagine like a moving proton. Imagine a moving H, basically. And if you can identify that, you're going to be able to quickly kind of discern between your acid and your base and really see like what's going on with this reaction. Let me pull up just an acid-base reaction and we'll just practice with that. Let's see. Maybe I shouldn't have done this as the last the last couple minutes. Okay, let's see. All right, we'll just write out this reaction. CH3, CH2. All right, and I'm going to quickly write this out. If you can identify the acid and the base in this before I can write it out, please feel free to do that. The goal with these sessions is for me to go through problems where I hope that you are working through them as well, so that you really get the practice that you need with these topics. Tonight, we did a little bit of everything tonight. If you would prefer just a more focused session next time, we can do that too. All right, so looking at this, if I'm imagining, I know this is an acid-base reaction. I want to figure out what's going on with this. So I'm looking at this. I know that the first thing, the first species loses this H between this and that, right? Something that loses the H, that is going to be my acid. So basically, I'm just going to imagine that this pops off and combines with H2O. Right? When that happens, it's going to create H3O plus. So whatever accepts that hydrogen is going to be your base. The acid becomes the conjugate base after it loses its proton. The base becomes the conjugate acid. The nice thing about these is you can also look at the reverse reaction. And the conjugate base, guess what? It acts as a base. This is going to gain an H to become the acid. So it goes both ways, just a good way to double check. All right, and we are out of time. Thank you all for being here. Thank you for asking questions. I hope it was helpful, but again, please be brutal. Give us some feedback so we can make these sessions better for you. The goal is just to be here to help you out. All right, so good luck this week. Hope everyone has a good